all of you have, I hope all of you have studied vectors after the last class, and also the elementary linear algebra that I have told to study this part. We discussed vectors also earlier, that what are vectors and how they have the displacement, how do they have the distance, okay? How do they have operations, different types of operations we mentioned, okay? And matrix also we discussed. We have not discussed determinants, and that's one part that I will discuss here, and I will go ahead. Okay, similar to matrices, determinants are scalar quantities obtained by the sum of products. Sum of products means when you multiply two numbers, you get one answer, and another set of two numbers you multiply, you get one answer. So when you add those multiplied both answers, then we are calling them as sum of two productive values. Alright. So we do that here in determinants. We say these quantities, scalar quantities obtained by the sum of product of elements of square matrix. Square matrix, that is rows and columns are equal, and their cofactors according to a prescribed rule. They help to find the adjoint inverse of matrices. For every square matrix, there will be C of I and J same. There is order n cross n, not n cross m, because n is same as row also and column also. This is how your matrix look like, and this is how your determinant look like. Its determinant can be shown like this. Okay, these are having the square values, and this having the straight lines. Okay, that's how you can recognize what is the matrix and what is the determinant. Okay, let's see the small calculation here. If you have a 2 cross 2 square matrix, okay, and the order is definitely 2 cross 2, A, B, and C, D. A, B, C, D, A into D minus B into C. Okay, the cross multiplication, and then it will be evaluated, and finally we'll get a one determinant value. So here is one of the example 8634 real example. How do you do that? You multiply 8 into 4 and 6 into 3 like this, and you subtract them here. Okay, 32 minus 18, that is 14. For any 3 cross 3 matrix, the square of matrix of order 3 cross 3 would look like this. Okay, programmatically, you have C equal to 1 determinant, that is 3 cross 3, and this rule I hope all of you understand. Okay. Keep multiplying the small determinant by the anchor number and by its sign. Okay. This you will keep as one of the quantity that will multiply. This is my, for example, A1. Okay. Then this 1, 2, 3, 4 is my matrix that I'll use it to calculate multiplication. B2 into C3. Okay. Minus C2 into B3. Okay. This one at this place actually, nothing is there. Alphabets are not there. Signs are there. I'm just talking about the position where the elements may be presenting. Okay. For example, we have A1 here, and here we have B2, here we have C2, here B3, here we have C2. Okay. If you have 3 cross 3 matrix, then you will do like this. The multiplication will change, and that's how you have one element ready to multiply, and another one is need to be calculated or evaluated. B2 into C3, C2 into B3, and you are going to subtract, and you are going to subtract with the same calculation. Same numbers. A real example here, 3 is being kept here, and -2 and 7, 5 and 8 need to multiply. So however, if I come here, then these 4 elements will be your one determinant. Okay. If you are here, then 4 and 2, 5 and 7 will be 2 of the elements. All right.
For that element, reviewing the row and columns. For that, correct.
Yes. For this one, rows and columns has to be ignored. Like if I consider 3, this row I will ignore and this column I will ignore. Only remaining elements I will consider. Right. Okay, that is the determinant.
So, it is some important on the space.
How can I help you? I want to look for free trial class. Last you to sign up. Start asking questions. Okay. I hope you understood what are determinants. They help to find adjoint inverse matrix to solve further to solve linear equations through the matrix inversion method. We need to apply this concept of determinants. Okay. The cross product of 2 vectors is remembered easily through a calculation of determinants, because vectors will be represented in terms of matrix. So to evaluate them, we can use the determinant method and we can solve those vectors. Okay, I hope all of you understood. Matrix method to solve a system of equations like Ax equal to B. Perhaps to solve this equation also we'll be able to use the determinants. So find A. If A is not equal to 0, then system has unique solution, and give x equal to A inverse of B. If A determinant is 0, if it is not 0, then the solution. If it is 0, then we have 2 options. Adjoint of A, B is not equal to 0, then system has no solution. If adjoint of A of B is equal to 0, then system has infinite solutions, and obtain by putting x, y, and z equal to k, where k is any real number that you can choose. Okay, so to solve such equations, there will be a method using determinants. That is a determinant, and other topics we already covered, and that is these topics what we are presently studying are mathematical knowledge that each student must have, which will attend this one. But unfortunately, everybody may not be knowing those things. That's why these topics have been picked up. Okay, just to show you and make you aware of what are things there which ML will be going to use. Okay, I hope all of you are very clear with the vectors. Okay, no problem. What do you mean by scalar?
Single magnet.
Single magnet. Only magnet.
Unit of measurement having only magnitude.
Okay. Vector for magnitude and direction.
Unit of
In
measurement having
two-dimensional vector is
yes,
three-dimensional
matrix.
matrix.
Three-dimensional is matrix.
Okay. How do you tell in terms of matrix? How do you write and how do I understand? How do I imagine that thing?
So X Y gets
Okay.
X Y X Y.
So in scalar we are having only magnitude, and in vector we are having magnitude and direction. Okay. So what is that first thing that we are having in the matrix?
So I hope first let us build your imagination. So everybody may not be having it. This is your y-axis. This is my x-axis. Can you show me where is z-axis? Yeah.
Let's go into the water.
Shall I take it down here?
Yes.
Okay, I'll designate them. This is y-axis, this is x-axis, and this is z-axis. Okay? If you want to imagine it, this is my plane, one of the plane, the board, that flat board as I'm showing, okay, x-axis. And if you want to see the third face of that, okay, you can take a similar angle here and you will extend this thing. Now you'll see that another angle is still there. Okay. So you can understand that by making the angle like this. This is your 90 degree with respect to your x and y. Okay. And this is your another angle that you are making with respect to your x and z. Another axis is there that comes from y to your z axis that I can draw like this. Understand? Okay. Okay. So I hope all of you understand this. Okay. This is a cube having a 3D space inside the box, right? Okay. Now, if I consider this my origin, so I will have three values. I have in my matrix three values. Values I have. So these values are I'm saying this is my vector. Okay. This is actually my tuple. This is actually my one of the tuple that I have represented in terms of matrix. Okay. And they are not the usual values, they are the coordinates of the plot in 3D space. That's why we were earlier trying to say vector space, vector space. What is that? This is the vector space that we are trying to tell you. Okay. These are your axes which are giving us the numbers on their axis each time. Right? But each, all of them are having individual numbers on their line. And if I ask each line one number, so these are my numbers which are ready. I am asking x value, it has given me 2, so I mark it 2. And y value has given me 4, so I mark it here. Z axis has given me 6, I'll mark it here. Now, when all the axes are giving me the value, they're not actually giving me the value, they're actually trying to create a point in the space. Right? They're trying to create a point somewhere here. Right? So that is my vector that I am creating with the help of these values. The dot is not a dot, it is a vector that I have created. All right. So rather than I represent this kind of a line graphically, we represent like this, right? Like this, and we say this is same as this one, equal to exactly. All right. That's why we call it as a vector space. And not only this one, I just spoke about plus y, plus x, and plus z. If I tell you about minus x, some value is minus is there, x value is minus, then it will definitely tell me that so this is minus 1, this is minus 2 that you have. Okay? Then I can say that I can also have my y-axis being available, right? And in that case, I also have my z-axis being extended onto the back side of the board. Okay, so this is my front side, and this is the back side of the board. So now I can see this is my x-axis, this is my y-axis on the plane. And this line is going inside the this point and extending the back side of this plane. All right, that's what make this z-axis available, to make this 3D point available in the 3D space of vector. All right, that is why we are calling this vector equal to this kind of vector. All right, I hope you understand this. If I only have the two x and y, then I will just have one coordinate having x comma y. That's the specific point. Now I will write here like this, and let's say that is my tuple. As you write in your Python, this is a tuple, right? This is how you write it. This is my tuple. All right, all the vectors that you represent are tuples. Now I hope all of you got it. Okay. I just drawn this this extended part so that you can understand what it is. Just to imagine how it exists. Okay, if I directly write it, you might not have got it. This is what should happen. All right, it's like a plus minus. This is positive side, negative side, plus minus. This is minus. Got it? Okay, so that's how we represent the vectors, and that's how I have to imagine whenever I say vector. In linear algebra, there can be several operations that can be performed on vectors, such as multiplication, addition, etc. Vector can be used to describe quantities such as velocity of moving objects. Some crucial topics encompassed under the under vectors: type of vector, dot product, cross product, addition of vectors. The operations. Okay. In the last class, we just gone through all the topics, and we just saw how they are applicable to real-time examples also. As we saw one example of from Hubli to Harvard, if I want to go, my displacement is 20. It's not 20 kilometers. The road that we have traveled, that we are going to travel, is 20 kilometers. If I take a plane and if I directly draw a straight line, then my distance will be reduced due to the curves of the road. I'm having a lot more time being incurred, and also the distance is being covered. All right. So that's how, even when you talk about any of your different villages or districts that you are reaching, you will tell this much kilometer in terms of roadways. Where via bus or via private vehicle we go, then we draw that distance. If I go via plane to any of the other nations, then the line is almost straight. Okay, then that distance is different. Airways is different. Roadways is different. All right. That's how we try to calculate the displacement with the help of vectors also. Matrices we spoke about. I hope you have understood the vectors. We keep it a separate place. Matrix is used to organize data in the form of rectangular array. It can be represented as m into n, and the same thing. Linear algebra matrix can be used to express linear equations in more compact manner. That's what tensors are also saying. Okay, linear equations could be transformed into matrices, and they can be the compact form of any equation. They say. Alright? Okay. And those equations could be solved with the help of determinants. So all of them are linked together. You just need to know by all of this, you just need to know what those concepts are and how can I use them in future. Okay? How can we use them? We'll see that later. Just understand what do they do and how can I take a small example like can I solve that? You should know how it is working. That's the required thing. That much is expected from you. Okay? It's already been studied by you, but as a brush up, we wanted you to have that in your temporary memory so that you can remember when I'm explaining that. Linear algebra and applications. Yes. I have a reason for not talking on this one. Anybody tell? You take it as assignment and explain. So where is the assignment? How many of you read it? Vinay read it yesterday. How many of you read it? No? In the links are ready in that. Nobody opened up presentations. Okay? Each text is having link. You are not taken a trouble to click on that also. Okay? It's also telling you how you can write it and how you represent it. Everything is there. We spoke about this one, right? Linear equations. What do you do? You study and get back to me. Yes. As I opened, I'll just explain one thing. What is a linear equation in one variable? When you have one variable, how does it look and how it is used? Linear equation in one variable is a basic equation used to represent and solve for an unknown quantity of one unknown value. It can be easily represented by graphically, and it's always straight line, obviously because other value is absent. It is absent, obviously it goes in one axis only. The linear equation is easy way of representing a math statement. Any variable or symbol can be used to represent unknown quantities, but generally variable x is used to represent a linear equation in one variable. So your x equal to a. So a is having some value. So y is missing. So that's why it is 0 only. The y is 0. Y 0 means this is the point it is having. This is the x-axis and y is 0. Alright, it is just pointing it down. This is not vector. A linear equation of one variable of the form ax plus b equal to 0, where a and b are any two integers and x is unknown variable that you have to find it. Having only one solution. Taking example, 4 added to a certain number gives 10. I repeat, 4 added to a certain number gives 10. So what is that number? Okay, find the number. How can we represent this problem in a simple way? We can represent x plus 4 equal to 10. This will go on the other side of it. We can represent like that. X plus 4 equal to 10. This statement can be represented. So now the statement converted into equation, not this one. Don't pass this one. General equation. 4 added to some number gives 10. This statement, English like this statement, could be formed with this kind of a statement. Is that right? Let's try to understand this. Statement and this one. 4 added to a number gives a 10. X plus 4 equal to 10. Is that right? Okay. So you need to find 10. We assign a variable to a number. and this is called an equation. It helps us with a large, large problems like this in shorter way. This equation has one variable called x and has the highest power of x is 1, definitely. And this kind of equation are also known as a linear equation in one variable because the degree of variable is 1. Okay. Now, how do you solve this? X plus 10 minus 4. X equal to 10 minus 4. That is 6.
Yes. Here the equation is called the linear because the degree of x is 1. Degree of x becomes 2, sir.
2 then 2 variables. I mean, linear equation 2 variables and degree 2. A linear equation in 2 variables is equation in which two variables have the exponent e, exponent 1, solution, or no solution, or infinite solutions, or many solutions. We can look at an equation here. Linear equation of 2 variable are algebraic equation which are of the form y equal to mx plus b, where they are the equations of the first order. Okay. For example, y equal to 2x plus 3 and 2y equal to 4x plus 9 are 2 variable linear equations. Then we have forms of equations, forms of linear equations. Standard form ax plus by plus c equal to 0. Slope intercept form y equal to mx plus c, and point slope form y minus y1 equal to m into x minus x1. The same equation in multiple formats. Again, the example is been given here. 3x plus 2y minus 11 equal to 0, and there are 2 unknown variables here. Earlier there was only one variable, which is unknown. And here also. All other values been replaced. I mean, what you can say, replaced with that, but with x and y need to be found out. The system of equations means the collection of equations. They are also referred to as a simultaneous linear equation that could be solved at a time. There are again a lot more details available, so that we can discuss more in detail about other topics. Okay, so you studied this in 10th before 10th standard. Okay, that's why I told you to revise. Nobody revised? Very bad. Okay, simultaneous linear equations, solving linear equations, solutions of linear equations, graphing linear equations, applications of linear equation, and straight line. You have studied x is called as x. Okay, that is same. Okay, mathematics is not more about English. So you read the English paragraphs, but the equations you will understand it. All right. Okay. You studied? Yes, linear algebra and its applications. I hope all of you have basically understood what is an equation. Equation, what is it? We spoke a lot more things, but what is equation?
Equation is a formula.
So what is formula?
It consists of variables and variables.
Okay. So what is this for?
So its value or values assigned to variable or variables.
Okay. why that word equation is coming, equal I sense it. Why is equation? Yes, whenever we have LHS equal to RHS, when we equate them, we have equation. What is formula?
Same as the common.
LHS equal to RHS. E equal to MC square. The same. That's what the formula, right?
Formula.
So how do you tell?
To find out the values. That is the
Okay. E equal to I guess after in RHS I add some values and I get value. So what is formula basically? Anybody?
Formula is a generalized equation, sir, which applies to all scenarios.
Others? Formula you have mathematical formulas. Yeah. Okay. Nobody knows? Relationship between? You're right. Near to that. So whenever you see an equation, all the equations are arranged in a specific manner. If you just disturb it, the variable you put it somewhere else, then the formula gets disturbed. Right? They have been arranged in connection with all of their relationship. I should say. Okay? It is an arrangement of variables in relationship with each other. Then they create a specific outcome based on the values that they are provided. The relationship between all the connected variables are very important. If you miss them, if you place them somewhere else, your values will not be right. Alright? The basic equations are very much important for you to understand. What is basically, whenever Sabyasachi sir says, basically, he says that meaningfully, he repeatedly says that. Researchers do that actually. He might research more and more. That's why he says that. Whenever he says basically, that means he has gone depth and you ask him whatever depth, he'll explain to you. Okay? That's how it is. I just want all of you to, whenever I explain the concepts, go in little deep in that and try to understand what it is. But in interviews also, whenever somebody asks you this kind of basic questions, and not any Python or any ML or any AI questions, then you should not be silent. Okay, you have read everything and you know everything, and you went there and when they ask this one and you just silent, not speaking. Okay, you can say, no sir, please ask Python, I'll tell. Whatever you ask, I'll tell. But not, right? So please understand, they will train you whenever you enter into companies, but you need to know the basics. That's what they are expecting. Linear algebra is used in almost every field. Simple algorithms also make use of linear algebra topics such as matrices, step-by-step procedure to solve the problem. Okay. Any real life example that I can have? As an algorithm? Can I call a process as an algorithm? Process. Okay. My problem is processor.
Solving problems.
Solving problem my the process. Okay. Okay. So algorithm is step-by-step procedure, a process of solving a particular problem with some mathematical equations or whatever logic you add. Okay.
So is it flowchart?
Flowchart is different. Flowchart is graphical representation of algorithm. I explain algorithm in terms of step-by-step English-like statements. When I say flowchart, I explain the same thing, no change, but by drawing some boxes and some arrows, I'll use them and explain. then I call it as a
So if flowchart is graphical representation of algorithm,
Right.
then what algorithm is of flowchart?
algorithm is a textual format of graphical user interface. Graphical user interface converted to algorithm statement, English statements. If this statement is true, then I go to the next box. That same thing you are writing in the steps, step 1, step 2, step 3. Writing that. It's same alternative this thing. But whenever we design a algorithm, we first design the graphical so that everybody can understand the flow. For explanation, it is good to represent in visual boxes. And those visual boxes are in green.
Whenever we say algorithm, we go to flowchart form only.
Flowchart, from the flowchart, we will come back to algorithms. And from algorithm, we go to pseudocode. Pseudocode is a false code. Means if you just copy paste the same thing in editor, it doesn't execute. But it's a small part of the code. And some of these statements are there which are not executable. But they are meant for explaining the code, how does it work. After pseudocode, we start writing the code.
Or when this algorithm is built in editors, it becomes the documentation.
Document it. So we just have this algorithm as blueprint of the whole process, start to end. What is happening inside, we'll be just looking at. Okay, signal processing. I hope you understand what is signal. Signal.
What are the conditions?
It gives
Conditions.
condition. Okay. Well, why signal is used is the first question. Why signal is used? Anywhere to transfer the information. If I give an example of traffic lights, what information you transfer?
So, to instruct an object to do or not to do something.
Okay. Like traffic signals will instruct the
I say stop.
uh,
The orange says be ready. Yellow.
Any other angle looking at the signal? In electronics, we say it's a means of communication, right? Okay. Can a flag on a ship becomes a signal? And there's no electronics in nothing. A red flag and green flag on a ship in the sea can also become a signal. Okay. So signal you identify. To identify. To identify, we need an indication. So we have an indicator. Signal will be an indicator of something. Okay, it represents something. Alright? Okay. So we are talking about signal processing. Whenever we send a message that recognizes something. Linear algebra is used in encoding. How about encoding? We understand coding. What is encoding? Encoding. Nobody in computer science. Nobody in network engineers.
So it converts text into coding.
No. Encoding.
What analog digital signals?
Analog to digital. No.
So it converts energy into signals.
No.
Yes.
Convert into code. Encoding is generic meaning of masking something. Masking something so that we can identify the signals properly and nobody else can identify the signals. Okay. We can also say it like encryption in other form. Since we are presenting the signal processing, we are saying linear algebra is used in encoding and manipulating signals such as audio video signals. Okay. You want to mask the audio signals, you can also mask it. I can mask the video frames, you can also do that. So encoding is just addition or incorporation of changes that you want to do. Changes you want to do, like audio changes you want to do. Like we have a software which manipulate the audio. So they will be using this one. Alright? Because they have components to vary, and how much you are varying, they'll be showing you that thing. And that's same equation itself. Okay. It is required in the analysis of such signals. Analysis, that is a signal analysis. Vinaya, signal analysis. You have a subject. No? Okay. Anybody else electronics? Enter. Yes. Yes.
This is principle of analysis.
There you have this one. Signal processing. Okay, no problem. Those who have learned networking, they understand that signal processing is nothing but adding or multiplying or dividing those signals based on the requirement of transferring that signal from one place to another place. Okay, processing basically. So I hope all of you understand communication. Okay, end-to-end communication. So whenever we transfer some information, there will be different types of information communication that happens. So here we are only talking about signal processing on any of the sides of the devices, or maybe receivers or maybe the transmitter. Okay. When you talk on a phone, you're actually audio, you're talking in the phone, and phone is listening to your audio, and it converts into signals. Now the immediate question comes to my mind is which signal? Analog signal. So the immediate next question comes, what kind of analog signals? So does it have name? It has radio signals. Okay. So it converts into radio signals, and through radio signals, you will contact the nearby towers. So they will transfer our information by receiving. If you are subscribed, you are subscribed to that antenna. If you are not subscribed to that towers, then it will not. It says I don't know who you are. You cannot recharge. Okay. If you are a subscriber of the towers, then you have a network available. If you are not a subscriber of the tower, then it doesn't know you and you don't know that tower. Alright, that's why we have a subscribers identity modules. Who is subscriber? You are a subscriber. So I need to identify who you are. So I have been, you have been given a identity. And there is a small circuit called a module. Circuit. Alright. So you have a subscribers identity module inside a phone. That is called SIM card. SIM is subscribers identity module. So that way you have been identified uniquely, and that ID will be attached to your signal. That this person has sent the signal. Your phone number as well as everything will be attached to signal, and that's one signal will be sent. And your signal will not be transferred to other person because we have attached that thing. ID. Alright, so to attach it and to manipulate your signal, we need to have signal processing that has been done with the relay equations. Got it? And from the antenna, how it goes, it's again long story. Okay, linear programming. It is an optimizing technique that is used to determine the best outcome of the linear. Several linear algebra algorithm to solve complicated problems, and prediction algorithms use linear models of equation that are developed using the concept of linear algebra. These are the applications of your linear algebra, and in detail we will look at the models in upcoming showing the modules. All right. Okay. We'll go next. Linear combinations. We just saw some definitions of one variable. Linear equation is one variable, right? This is not x2. This is subscript x2. Whenever you read it in that, you read it that way. You already know this one. That's why I'm coming here. A linear equation with the one variable is an equation with only one variable. Example: x plus 3 equal to 6. What is x now? 3. Yes. This is very simple to solve. Linear equation with the two variables is something like this: x plus 2y equal to 3, where there are two unknown variables x and y. There's 5x plus y equal to 17, 3x plus y equal to 15.
Adding.
Adding.
And the second equation is substitution. So you will get 2x equal to 2, so x equals to 1.
So 5 minus 3.
Yeah, 5x minus 3x.
5 minus 3 is 2.
2x. Y.
Y and y
Cancel each other.
cancel each other. So I have 2x
Equal to 4.
equal to 17 minus 3, that is 2. So I have 2x equal to 2. X equal to 1. 2 by 2. Okay. Next, there are more than one way of solving the system of two linear equations. Many people. Okay, how do you solve the y there?
Adding x into the any equation.
Any one equation? Add 1 to any of the equations and see. 5x plus 1 equal to 17. 5x plus 5x equal to 17 minus 1. 3 point something. Okay, 17 by 16 by 5.
3.2.
3.2. Okay. Okay. One variable equation expressed in terms of other one. Y equal to 17 minus 5x, and then substitute into other equation. Then you get a y value also, like we did. Okay. This is not a linear combination method. We just solved it by replacing or simultaneously solving for both the equation by subtracting both the equations. Okay, the linear combination method is precise way of or precise way of solving these kind of equations. Linear combination, using linear combination method, a system of two linear equations is solved by combining two equations by eliminating one of the variables. Like we did combined two equations and we eliminated one of the variable, that is y, and then we found out only x, and then we substituted the x value into the other equation. That's what is said to be linear combination definition. A linear equation with the two variable x plus 2y equal to 3, where there are two unknown variables, 5x plus y equal to 17. Separately, the example has been taken. Combining two equations to eliminate one variable, that's one step. Once one variable is eliminated, an equation with only one variable is left, and the value of the other variable can be determined. We did that, and this answer can be substituted into one of the equation to give a value of the other. All right. All right, understood, or shall I do an example? Okay. I was expecting. Okay. Tell me an equation. What is that? 5x. 5x plus y. Next.
X plus 2y.
Ax plus y. Then what it says, combining the two equations, eliminate one variable. So this is done. Next. Huh?
Both are positive signs.
Both are positive.
Yes.
We cannot subtract.
Sir, usually minus sign is below the signs. Opposite signs.
Okay.
Here
Next. Here also.
below the three.
Below this. This is also plus, right?
This is also.
Okay, one of the variable is eliminated. An equation with only one variable is left, and the value of the variable can be determined. Okay, then 2x equal to okay. Next further, what is the last one? This answer can be substituted into one of the equations to give you your value of other variable. How about the next one?
5 into 1.
5.
Sorry.
Next.
17 by
5. This is 5.
5 is 7 minus 5.
Okay. So we have both the values only. Combination of columns of vectors. Like I told you, there will be one row and column matrix. That one row vector or row vector, that is a matrix that have only one column or only one row. One column, one row, and one vector representation. As I just wrote 2, 4, 6 as one vector in square brackets. There is one vector. You can write it vertically or you can write horizontally. That's how it is represented. Okay, that's one here. Let's get back to the reference. Linear combination of vectors. We have let A1, A2, and A3 be 3 cross 1. Is this 3 cross 1? 3 rows, 1 column. Vector defined as A equal to 0, 1, 2, all the values. And now all of you understand what these values represent. Understand? Now all three values represent something on the plane. In a cube, that box. Alright? Okay. Okay, we have A1, A2, A3. Let B be another column vector defined as B. And B is a linear combination of A1, A2, and A3. In order to answer this question, note that the linear combination of A1, A2, A3 with coefficient alpha 1, alpha 2, and alpha 3 has the following formula. Alpha 1, A1, so all of them are added equal to alpha 1 dot product with vector plus alpha 2 dot product, and that could be end up having this equation. A1 dot 0 plus A2 dot 1 plus A3 dot 1, that is one row completed. A1 dot 1, A2 dot 0, A3 dot 0. One row completed. A1, 2, A2 minus 1, A3, 0. Another row completed. This is get cancelled because of 0. And both the A2 multiplied with 1, alpha multiplied with 1 remains. So alpha 2 plus alpha 3 remains. Or you can call them lowercase a or lowercase b also, whatever symbol you want to represent. Okay, that looks like this. Now B is a linear combination of A1, A2 and A3 and only if we can find this alpha 1, alpha 2 and alpha 3 such that B will be equal to alpha 1, A1, alpha 2, A2, alpha 3, A3, which is equivalent to this one. Equivalent to this one. Means this, whenever you find out, if you substitute any value, it must become 1. Any value if you add it here, that must become 1. Okay. With this one, this alpha 1 is 1. Okay. And if you substitute alpha 1 and alpha 2 here, you should get 1. That's what it is saying. Two vectors equal. Okay, but we know that two vectors are equal if and only if their corresponding elements are equal to each other. You can see we are just wrote whatever we just now told as a statement. We just wrote it as an equation here. A2 plus alpha 2 plus alpha 3 is 1, and this is also 1. This is also 2. The second equation gives us this one gives us the value of first coefficient. Is that right? If I replace or if I substitute this alpha 1, okay, where should I substitute? Equation 1? Equation 1 is not possible. Second equation gives us the value of the first coefficient actually, that is ready. First coefficient value is ready. Next, by substituting this value in the third equation actually, we can get started third equation because A1 is available in the last equation. So 2 into alpha 1, that is your 1. Okay, 2 into 1 is 2 minus A2. Alpha 2 equal to 1. So now alpha 2 equal to 1. What is the value? One. 2 alpha minus A2 alpha 2. Tell me. What is that? We have three equations. I make them as A2. Then we have A1 equal to 1 ready. Then 2A1 minus A2 minus A2. Now I want to replace this one. This is my equation 2. This is my equation 3. This is my equation. So I want to add this equation 2 value into this one. This is minus
2 into 1.
2 into 1. Then
2 minus 1. 2 minus 1.
2 minus 1.
Yes, sir.
Is that right? Okay. Both sides?
Both side minus same cancels.
Okay. This minus? Finally, we have
Minus 2 plus 1.
obviously this minus goes there, and you have minus 2 and plus 1. So what is the answer? Minus 1? No?
Sir, minus A2 equal to minus 2 plus 1. Sir.
Minus A2 equal to
Minus 2 plus 1.
minus 2
Plus 1.
plus 1.
Minus A2. Sir.
Minus A2. Here,
Both sides.
both sides. Then
Minus
A2
2
is-
plus 1.
A2 is equal to 1. Okay, now we have A1 ready, A2 ready. You can find out the last one. that is A2 plus A3, A2 plus A3 equal to 1. So A2 is 1, so 1 plus 3, that is plus 1 plus A3 equal to 1. 0. What it is saying it is 1. A2 plus A3 must be equal to 1.
A2 is 1, sir.
It is also A3 is zero.
A3 is 0.
A2 is
1.
A3.
0.
A3 is 0.
No, sir. A3 is
A1 plus A3 equal to 1.
only
Move this one to that side. Minus 1. 1 minus 1. Is equal to 0.
A3.
So the assumption is wrong in that case.
So it's correct.
No, India actually. I said here, if and only if we can find out these values and which is equivalent to this, ideally we have considered, and that's why this considered value, two of them are true. One of them is
That is not
huh?
Sir, that is
It is also one only one.
Which one?
Equation 1.
A2 plus A3.
Yes, sir.
Add A2 plus A3. Is it 1?
Yes.
The variables are only 0. Okay. So equation is same only. Okay. But we know that two vectors are equal over here. Okay. Finally, by substituting the A2 in the first equation, we'll get A3 equal to 0. Okay. Finally, we have this matrix is being available, that is B. Therefore, the answer for the question is affirmative. This is the linear combination of vectors. Okay, so linear equations is solved, but the involvement that was there of the variables are vector values. I hope you have understood. You have taken three matrices, and then you combine and made it as one equation, sir, like this. You formed. Initially, you have this kind of matrices, became equations, and then you solve them. With this one, you solve them, and they became the answer, that is P. Okay, that is solved. 3 cross 2 matrix A1 A2 as follows. Let A1 equal to 1 by 2 and alpha A2 equal to 1. B2 scalar quantities. Compute the linear combination. How do you do this? Compute the linear combination, combinations.
For A1 multiplying 1 by 2, sir. And A2 multiplying by minus 1.
A2 multiplied by 1.
alpha 1 is half, sir.
Alpha 1 is this half. 0 by half.
0 by half is 0, 0.
Uh,
That 2 by half is
1.
That's 1, sir. Again, 2 becomes 1, 0, 0, 0 for the existing matrix of A2, sir. Because scalar is 1 here.
So
this is A2 is 1. So this will be same matrix will be there. Further,
Corresponding values have to be added, sir. 0 has to be added with 1, that becomes 1, sir.
okay, is this right?
Yes.
So it becomes 0, 1. This is right. Okay. So then you're going to add them. Obviously, this equation follows. Same thing is being replaced. So since we don't, we have been given these values, we just replacing with those values with these values 1 and 1 by 2 as A1 and A2. A1 and A2 have been replaced with the matrices. I mean that is vector, and we have the multiplication happened, and we have a resultant matrix available. We added them, and we got a resultant matrix. That's what we are trying to understand. The two matrices define two. Finding out the combination of two vectors with the help of linear combination of equations. That is the linear combination of vectors. Understood? Linear transformation. A linear transformation can be seen as a simple function. I hope all of you have discussed. We all discussed what is the function, what is simple function, and how it varies based on the different values that you added and different variables involvement. Here we are mentioning we usually have a scalar value as the input to our functions. Okay, single values. But rarely so far we have experienced that the input into a function can be a vector, like a matrix. That's how we did that. We're saying to a function of equations, there might be earlier we just have one value, individual value we will be getting. That individual value in terms of vector discussion, we said it as a scalar, only one value. If you have multiple values, vector. Single value, we go scalar. So we are saying here, whenever you have an equation earlier, you are just having one value as an input to the variables. And it is coming there and it's solving the equation. Now we are saying, now in the further functions, we will not be getting only the individual value, we will be getting a matrix as a one of the value added to the equation. Alright, that will become one of the values. But really so far we have experienced that the input into a function can be a vector. Okay, so a linear transformation is actually a function that maps an input vector into an output vector. You give an input and the equation getting solved, and the output is also a vector only. Okay. In your individual values, you are actually getting the individual values answer. You are adding one individual value, like 2 into 1 you are adding. One is my individual value, I call it a scalar value. I am getting an individual value. But when I am using my replacement or substitution with the vector, we are saying here the result is vector only. Alright? Okay. We have some diagram over there. We just do this. For linear transformation, both input and output vectors are often the same of the same length because they don't change their value. I mean their magnitude. One of the most famous example of linear transformation is a discrete Fourier transform. Heard of this? Have you seen any equation of discrete Fourier transform? This transformation takes as an input sequence of n signal samples, and these samples are then mapped with the Fourier transform into a sequence of another n samples. And these new samples are actually complex numbers in Fourier transformation domain or Fourier space. With complex numbers, we can capture the amplitude. I hope all of you know amplitude. We're discussing it. With the complex numbers, which also has an imaginary part, we can capture the amplitude
by drawing the wavelength from
trying to draw and the topmost point. If I measure it, that's my amplitude. Okay. With complex numbers, we can capture the amplitude in the frequency domain and phase, that is time shift of our original input signal. What is this frequency domain? Frequency. In 1 second.
wavelength as the frequency. In 1 second, how many wavelengths?
Number of cycles per second.
Okay. Wavelength will come.
Number of oscillations.
Number
of oscillations per second.
Number of oscillations.
Okay. So what you're saying? We are saying number of signals. For example, this is my one signal, and this is my 1 second. Number of oscillations 1 second. So this is my one cycle in 1 second. Right? This is my frequency. You mean the same signal. In same 1 second, so many signals I can draw. Okay, so I have one 2. I have 2 cycles in 1 second only. Okay. I can also increase my number of cycles in 1 second. Okay. So how many number of, here it is 1 cycle, here it is 2 cycles. So on, I can increase number of cycles. Right? 1 positive, 1 negative will make 1 cycle. Okay, circular actually. If you combine it, it becomes circle. Alright. We prove that with the help of angles that is splitting. If you take this and put it here, it will become a circle only. Alright, that's 360 degree circle. So that's why we say when it rotates from here to here, that means 1 cycle completed. 1 rotation of the circle completed. This. Okay, that's one discussion. We are saying frequency domain. We can try to find out the amplitude in the frequency domain. Whenever we have the signals available, so we will have the amplitude. So this one we wanted to find out. And whenever you talk about signals, we have multiple types of signals. Okay. Why we are talking about signals and why we are talking about complex number is whenever we have signals, as I am telling you, like this, as I am telling you, this is my amplitude. This is my plane. Board is plane. This is my x-axis. This is my y-axis. Okay. This is my, for example, voltage. This is my time. Right? With respect to my time, as I wrote 1 second, this is my 1 second device. This is my x-axis. This is my y-axis. As you already know that you have x and y-axis. I can also draw z-axis. Agree? So if I can draw z-axis, I can draw that z-axis like this. Okay? And I can make a that imaginary part, which is z-axis minus z-axis. I can go behind also. Okay? That part we are talking about here. These new samples, okay. Sequence of n signal samples, and these samples are then mapped with the Fourier transform into a sequence of another n samples. These new samples are actually complex numbers. Complex numbers. As we told, those complex numbers represent one of the points on the plane. As we draw the curved lines, because those points we just combine, but there are points only available on all the curves, right? So we are talking about those points as a values. Those values are the complex numbers. One number. Fine. Okay. With the complex numbers, we can capture the amplitude in the frequency domain and phase shift. So that is my phase shift of 90 degree. All right. My z-axis has a drawn, and my y-axis is making 90 degree shift. We shifted. Okay. Of our original input signal. Our original input signal is the board's plane, and the transformed signal is just tilted 90 degree. Got it? That's all. We just try to manipulate these signals. And here you just see signals, those lines are not there. The dots that I have drawn with the arrow are available. So understand with the dots and imagine the cycles in the by connecting the dots, blue dots on the line. So we'll draw it with the mouse cursor. Okay, here it is getting started, and it is getting started from here, and it is getting down here is a minus signal, and I am having the next signal being coming here, and I have the whole signal being stopped here. All right. Okay. Mapped into discrete Fourier. Okay. Let's discuss for 1 minute what is a discrete Fourier transform. Okay. Discrete Fourier transform are calculated for sequences of finite length, while DDDF are infinite length. That is your time series. Discrete time Fourier transform is different, and DD. Okay, we will not go the difference. Okay, they have explained the difference. We don't need a difference. This is the formula for discrete Fourier transform. Okay, we'll finish it here only. We'll not go much detail in that. It's a paramount importance in all the areas of digital signal processing. It is used to derive a frequency domain. It is used to derive a frequency domain, that is spectral representation of a signal. I hope all of you understand what is spectral. Something as a spectral, you mean that they look like ghosts. She's comparing a spectral to just representation or indicating something. In terms of physics, spectral is a band of wavelengths. Okay,
Or we can take it as a range.
range. Yeah, you can take it as a range also. It is used to derive a frequency domain, a representation of a signal. So that we can represent with therefore this concept. In OpenCV, I hope all of you have heard of OpenCV from me earlier also. That is used to handle the image processing. Okay, as well as video analytics, OpenCV, machine learning library. Fourier transform is used in analyze the frequency characteristics of various filters. Filters from OpenCV. For images, for 2D discrete Fourier transform is used to find frequency domain. A fast algorithm called a fast Fourier transform is used to calculate the DFT. That is your discrete Fourier transform. Alright. So any media that you are handling, media, photo, video, audio, the medias. To handle that thing, you are going to manipulate that thing also when you take that thing as input. So to manipulate that, you have this discrete Fourier transform available for you handy as a tool to manipulate those things with the help of this frequency domain variation. Okay. For example, if you want to manipulate your color image to black and white, okay, there is a frequency that will be manipulated. That's one method, and there will be different channels available, and those RGB channels. Along with that, there will be a black, and those channels can be modified. Okay, and you can also make it a grayscale by removing some of the channels. What is DFT image processing? Okay, here we can see an example, and we also see a small demo here of the graph. Discrete Fourier transform represents an image as a sum of complex exponential of varying magnitudes. Do you understand this one? Varying magnitudes. Okay, like a variation of the graph happens. And frequencies as well as phases. Square function as an image representation of square, while the natural images are the image representation with a rich local covariance. Covariance. Yes. Covariance. Covariance means it is a variation in the local of the point that you are considering. Like if we take an example of this one. One dot exists in a photo. There's a light dot exists on a photo, and that we want to represent in a 3D space. How do we represent? This is how we represent. As we told, spectral. This is how the spectral could look like, and we're saying an explanation They are the sum of means totally the sum of all the complex numbers which are varying in amplitude, the height and this one. Okay, so this is a 3D space having the vector, and if you zoom it looks like this, and that has been constructed here with all the four these bumps you can see here. That's how you can just see that the classes. Okay, here you can see the division is more in number, and that's why the things are there. And at the beginning, at the middle, it is straight. And there are so many parts are there, so that's why it is making it one of the amplitude. All right, all of you understood what is the transformation? It's just trying to transform with the help of its manipulating capacity of what you can say the spectral frequencies and what you can say amplitudes. What is Fourier transform in ML machine learning? The Fourier transform is a way of splitting something up into a bunch of sine waves. What does it mean? It's a way of splitting. That means I can handle splitting something up into a bunch of sine waves. I can produce it. So that's how your Fourier transform will help you in manipulating the media that you are sending. All right, we are talking about in terms of machine learning as well as your AI. We can do an example of that and produce such kind of a graph, a plot, with the help of the matplotlib and SciPy. Okay, because with that we'll be able to have the cos numpy available, and we have array arrange also, that is array actually 0, 8, this a range actually, a range, you read it as that. Okay, a time example shows how sequence of samples from a time domain is mapped into a frequency domain using a discrete Fourier transform. We just saw earlier some equations. That was an equation that has been used to show that this is a cos 2 into k into np dot pi. Np is numpy dot pi value is just 3.42 divided by 4. It will give you these points, individual points, and those points will be taken in x, and that's what we are going to pass it as a parameter to PLD, that is plot dot stem k comma k is your range. We have 8 points. 1, 2, 3, 4, 5, 6, 7, 8 points. So this is my A range. Earlier I have only range, which was producing 0 to 8 numbers, starting from 0. So now I have A range. So I have 8 numbers available here, 8 points available here, and this is my X, which is holding the positions of those values. The real-time positions of those values in the space. And I use line collection as 2. Line collection is the connections between the values. All right. Okay. We'll just do this one and we'll stop here. We'll just do this one and we'll stop. Import all the packages NumPy, SciPy, and Matplotlib. Most of you have done that. Stop. Okay. The next class we'll go ahead and talk about input vector. We will supply. It's going to give us the output as a vector only. That thing we'll discuss. All right. Okay. Any questions? Any questions? No? Bring out that assignment.